Permeability in fluid mechanics and the earth sciences is a measure of the ability of a porous material to allow fluids to pass through it. Permeability. Permeability is the property of rocks that is an indication of the ability for fluids to flow through rocks. High permeability will allow fluids to move rapidly through rocks. Permeability is affected by the pressure in a rock. The unit of measure is called the Darcy, named after Henry Darcy. Sandstones may vary in permeability from less than 1 to over 50,000 millidarcies. Permeabilities are more commonly in the range of tens to hundreds of millidarcies. A rock with 25% porosity and a permeability of 1 md will not yield a significant flow of water. Such a Euro rocks are usually artificially stimulated to create permeability and yield a flow. Units. The SI unit for permeability is m2. A practical unit for permeability is the Darcy, or more commonly the millidarcy. The name is in honor to the French engineer Henry Darcy, who first described the flow of water through sand filters for potable water supply. Permeability values for sandstones range typically from a fraction of a Darcy to several Darcies. The unit of cm2 is also sometimes used. Applications. The concept of permeability is of importance in determining the flow characteristics of hydrocarbons in oil and gas reservoirs, and of groundwater in aquifers. For a rock to be considered as an exploitable hydrocarbon reservoir without stimulation, its permeability must be greater than approximately 100 md. Rocks with permeabilities significantly lower than 100 md can form efficient seals. Unconsolidated sands may have permeabilities of over 5,000 md. The concept has also many practical applications outside of geology, for example in chemical engineering. Description. Permeability is part of the proportionality constant in Darcy's law, which relates discharge in fluid physical properties to a pressure gradient applied to the porous media. Therefore, where is the superficial fluid flow velocity through the medium, is the permeability of a medium, is the dynamic viscosity of the fluid, is the applied pressure difference, is the thickness of the bed of the porous medium. In naturally occurring materials, permeability values range over many orders of magnitude. Relation to hydraulic conductivity. The proportionality constant specifically for the flow of water through a porous media is called the hydraulic conductivity. Permeability is a portion of this, and is a property of the porous media only, not the fluid. Given the value of hydraulic conductivity for a subsurface system, the permeability can be calculated as follows. Where is the permeability, m2, is the hydraulic conductivity, ms, is the dynamic viscosity of the fluid, kg/μs, is the density of the fluid, kilogram per meter 3, is the acceleration due to gravity, ms2. Determination. Permeability is typically determined in the lab by application of Darcy's law under steady-state conditions or, more generally, by application of various solutions to the diffusion equation for unsteady flow conditions. Permeability needs to be measured either directly, or through estimation using empirically derived formulas. However, for some simple models of porous media, permeability can be calculated. Permeability model based on conduit flow. Based on Alan Hazen, permeability can be expressed as where is the intrinsic permeability, length 2, is a dimensionless constant that is related to the configuration of the flow paths, is the average, or effective pore diameter, length. Intrinsic and absolute permeability. The terms intrinsic permeability and absolute permeability states that the permeability value in question is an intensive property, that it is a function of the material structure only, and explicitly distinguishes the value from that of relative permeability. Permeability to gases. Sometimes permeability to gases can be somewhat different than those for liquids in the same media. One difference is attributable to slippage of gas at the interface with the solid when the gas mean free path is comparable to the pore size. See also Knudsen diffusion and constrictivity. For example, Measurement of permeability through sandstones and shales yielded values from 9.0 x 10 a 19 m2 to 2.4 x 10 a 12 am2 for water and between 1.7 x 10 a 17 am2 to 2.6 x 10 a 12 am2 for nitrogen gas. Gas permeability of reservoir rock and source rock is important in petroleum engineering, when considering the optimal extraction of shale gas, tight gas, or cold methane. Tensor permeability. To model permeability in anisotropic media, a permeability tensor is needed. Pressure can be applied in 3 directions, and for each direction, permeability can be measured in 3 directions, thus leading to a 3x3 tensor. The tensor is realized using a 3x3 matrix being both symmetric and positive definite. The tensor is symmetric by the Onsager reciprocal relations. The tensor is positive definite as the component of the flow parallel to the pressure drop is always in the same direction as the pressure drop. The permeability tensor is always diagonalizable. The eigenvectors will yield the principal directions of flow, meaning the directions where flow is parallel to the pressure drop, and the eigenvalues representing the principal permeabilities. Ranges of common intrinsic permeabilities. These values do not depend on the fluid properties. See the table derived from the same source for values of hydraulic conductivity, which are specific to the material through which the fluid is flowing. As far as soils concerned, typical ranges of permeability coefficient for different soils can be found on geotechdata.info database. Source, modified from Baer, 1972, see also, hydraulic conductivity, hydrogeology, permeation, petroleum geology. Relative permeability, Klinkenberg correction, electrical resistivity measurement of concrete, footnotes. References, Baer, Jacob, 1972. Dynamics of fluids in porous media, Dover. ISBN 0-486-65675-6, Wang, H.F., 2000. Theory of linear peroelasticity with applications to geomechanics and hydrogeology, Princeton University Press. ISBN 0-691-03746-9, external links, graphical depiction of different flow rates through materials of differing permeability, web-based porosity and permeability calculator given flow characteristics, Florida method of test for concrete resistivity as an electrical indicator of its permeability.